Hello all and welcome to this video where we continue to look at integration and antiderivatives. In this case, this video we're going to continue to look at some indefinite integrals of a couple of functions that we have come across. So just a reminder from the previous video, a indefinite integral would be, when you find it or you're trying to find the indefinite integral, it would be the family of functions that if you differentiate it, you're getting what you've started with. So to clarify is, if we're trying to find the indefinite integral of this, is what are the original functions that if we differentiate, come back this way, we get this. So pretty much the definition of an indefinite integral is differentiation in reverse, or what is the original function we need to differentiate to get what we have. So that's what we're looking at. So a lot of this video is going to be based around looking at a differentiation rule and then just being able to apply that in reverse. Okay. So this is where VCAR in particular likes to get a little bit tricky, is that a bunch of the rules that we're going to look at, you aren't given explicitly. You have to sort of be able to look at, or the formula, you aren't given these formulas explicitly. Like, you aren't given this formula on the VCAR sheet, but if you technically worked sort of the chain rule in reverse, you'd be able to find this. This one, it's a bit easier to remember. It's just easier to remember. Some of the other ones later, I'll show you how you could look at the formula sheet and work backwards. Right. So as it says here, this above formula just extends the rule of anti-differentiation. So we started with a x to the n, or we just started technically with x to the n, integrated that, so we added 1 to the power and divided by the new power, which we got x to the n plus 1 divided by n plus 1, and then we had a plus c on the end. Okay, now we're just expanding this, where this x now is some linear subfunction, okay, which still applies the same thing. We're going to add 1 to the power. So we started with n power, we're going to add 1 to the power. We're also going to divide by that new power. But the only thing that's new in this is we're putting an a out the front. That's the only change that's in this one. So instead of x to the n, we've now got ax plus b to the n, so it's a linear subfunction. Exactly the same. Add 1 to the power, divide by the new power, but also whatever the coefficient is, stick it in front. Okay, so let's get straight into a couple of examples. We have 2x minus 4, so we want to find the indefinite integral of that, and we're going to do dx, and that's going to be equal to, we have 2x minus 1. Now we're going to add 1 to the power, so that becomes 5. So we're going to divide by the 5. And then also whatever the coefficient is, we're going to put that at the front. So 2 times 5. So that is now equal to 2x minus 1 to the power of 5 divided by 10. And that's all you have to do to use that rule. Add 1 to the power, divide by the new power, but also put the coefficient in front. 3x plus 2 all to the power of negative 3. So the indefinite integral of 3x plus 2 to the power of negative 3 with respect to x is equal to, well, we put our original function. We're going to add 1 to the power, so negative 3 plus 1 becomes negative 2. So we're going to divide by negative 2. And our coefficient is 3. So we're going to also put that down the bottom as times by 3. So we get 3x plus 2 to the power of negative 2 divided by negative 6. Now, using your index laws, you could rewrite this as 1 on negative 6, 3x plus 2 squared, but it's not asking for it in specific form, so this answer on the left would be completely acceptable. Right here, so that's just using that. That's one that you're going to want to remember. You're not given on the formula sheet, and trying to work backwards to derive it yourself during the middle of the exam is not great. So that's one you're going to have to put away in the memory bank just by using it over and over. Right, let's get to some of the ones that we are given. This one, this rule, you are given on the formula sheet. And it comes from, well, the derivative of log e to the x is 1 on x. So that's differentiating going that way. So if we go in reverse and anti-differentiate 1 on x, that's going to be equal to log e to the x plus c. And I forgot to say, why are we doing this? This whole rule works in all cases when this is a linear subfunction inside for any n value except 1. Except, that should say except negative 1. Okay. N cannot be equal to negative 1. Okay. And so that's what this slide is all about, is when n is equal to negative 1. So we're trying to figure out what happens if a dx plus b is to the power of negative 1, which is the same as 1 on ax plus b to the power of 1. So we want to look at the most simple form of that, which the more simple form is just 1 on x, which we've dealt with. If we differentiate log e to the x, we get 1 on x. So if we anti-differentiate 1 on x, then we get log e to the x. So what happens though if we go back to our original case that we want to deal with, if we've got this linear subfunction all the way up here? Okay. We have ax plus b all to the power of negative 1. Well, we get this rule here. We can write it as this fraction, which looks very similar to 1 on x, and we get the integral of that, or the antiderivative, is equal to 1 on a. So again, this coefficient comes out the front down to the bottom into the denominator, and we get log e to the ax plus b. But we don't have brackets, we have these straight lines, and these straight lines are called modulus or absolute value. And what happens is anything inside that, once you solve, like this could have been maybe 3 times 2 plus negative 15. Once you solve this and get into a number, this absolute sign or modulus sign means whatever's there has to then be converted to a positive value. So the modulus of 2, well, that's already positive, so it just stays as 2. The modulus of negative 2 becomes positive, so it just becomes 2. So that's what those signs mean. Yeah. So the antiderivative of 1 on something is 1 on the coefficient log e absolute modulus of what this original bottom bit was. So let me try and put some color in here to make this a little bit easier to see. Whatever's in the bottom goes there. Whatever the coefficient goes as a fraction out the front. And then of course we get our plus c. Now over here, I made the mistake. In all of these I forgot plus c. Needed plus c in all of those. Right here we go for time. 8 minutes in already. So let's apply a bit of this practice. So I'll write quickly over here just as a reminder, the antiderivative 1 on ax plus b is equal to 1 on a log to the base e absolute value of ax plus b, and that's all plus c on the end, of course. Okay, but straight away we're running into an issue. We have a 2 on the top, we don't have a 1. What can we do? Well, this is where we can use that scaling factor idea, where the antiderivative 2 on 1 minus 2x regard to dx is the same as the antiderivative 2 times 1 on 1 minus 2x dx. And since this 2 at the front has no variable with it, we can now write that as the antiderivative of 2 1 on 1 minus 2x dx. Now we've got an antiderivative that matches one of our rules, so we can use it. So we get 2 bracket 1 on, and let's also rewrite this as 2 1 on negative 2x plus 1, just to get it again. Matching formula a bit easy to use. So our a value is negative 2, so we're going to put negative 2 there. Log to the base e of negative 2x plus 1, absolute value, plus c. Okay, bring this 2 inside, so we get the 2 times by that, and that just becomes negative, and we get log e to the negative 2x plus 1 in the modulus. And now we also have to multiply the 2 times c. Now c is just from placeholder for any constant. Okay? It can be any number, and then we're going to double it. And since c is just a placeholder for any number, well, we could technically sort of say that 2 times c is, I guess, c, a new c. So you can get away with actually writing just plus c again, because c is a number, and well, didn't matter what the old c was, we're still just going to multiply by 2. We're just getting some random number, and reminder that c is technically equal to any number. It's not just a single number, it's a placeholder for any number. We can do that, we can cheat a little bit. Example B, we can, we've told dy dx is equal to 3 on x, and that we've given some initial information that when y is equal to 5, x is equal to 1. Find the expression for y in terms of x. So when it's asking to find the expression for y in terms of x, well, technically we should say equation. It's asking you to anti-differentiate. We're given dy dx, we need to find out what y equals in terms of x. So we want to anti-differentiate 3 on x with regards to x, and that's going to equal 2. And same thing, we can bring that 3 out the front as a scaling factor. We get 3 1 on x dx. That is equal to 3 times by the derivative of 1 on x is just log to the base e of x plus c, which is equal to 3 log e to the x, and you can still write it as plus c. Now we were told when y is equal to 5, x is equal to 1, so we can sub that information in. I'll just write it in coordinate form. So we're given 1, 5 needs to be true. So we get 5 is equal to log to the base e of 1 plus c. Now log e to the base 1 is equal to, if I can get my brain to work for a second, log e to the 1, that's saying e to the what is equal to, that's just going to be e, isn't it? Let's double check with our calculator. Where's the keyboard? Ln is log to the base e of 1 is, no, equal to 0. Oh yeah, e to the power of what will give me 1. That's right, we could rewrite this as, question mark, e to the power of what gives me 1, well, it has to be 0, so we get 5 is equal to 0 plus c, so c is equal to 5. Therefore, we can finally say that y is equal to 3 log e plus 5. So we did that. Now I'm just double checking. I'm guessing I've put this in here because there could be a gotcha when. Let's go back. Derivative of 1 on x is just log e to the x. There's nothing special about that. Yeah. Okay. Let's do it again, but we're told x is equal to -1. So the integral of 3 on x dx is equal to, we figured out 3 log base e of x plus c. We're going to sub in x equals -1, y equals 5. So we get 5 is equal to log to the base e of -1 plus c. So log to the base e of -1, I don't think that has a solution. Yes, has no solution. The only way that this could work is Technically, try and make it a negative. We might leave that and we can discuss that in class. Yeah, we'll leave this one. Right, a couple more things with this. We're up to 15 minutes already. Okay. All of these is when we could simplify or use the scaling factor as when we just had a constant in the numerator. But sometimes, of course, VCAR being VCAR, like to make it a little bit more complex, and they're going to put a linear term in the numerator as well. Now, we have seen this before. This is technically I guess a hidden hyperbola. So just like when we did hyperbolas, we want to change it into the normal hyperbola form. We would have been used to seeing it as, this is very similar to the regular hyperbola form, but we would have written as b x plus 1 plus the a at the end, and we would have thought that a is sort of a k in a vertical translation. But this is, so if you can remember how to convert it, what we want to do is we need to rewrite this 2x on x plus 1. We need to rewrite it as something that is x plus 1 on x plus 1, and we need to add some things in the numerator here that would turn that x plus 1 into 2x. Well, clearly we need to put a 2 in the front because we need to get the 2x, but when we expand this we'd get 2 times 1, so we then also need to add a minus 2 on the end, and we now split that out. We now get 2x plus 1 on x plus 1 minus 2 on x plus 1. The x plus 1 top and bottom cancel, so we are left with 2 minus 2 on x plus 1. And now we can use our anti-differentiation rules that we've just covered to go over this. So find the derivative. Well, the antiderivative of 2x on x plus 1 is equal to, we just showed that 2x on x plus 1 is the exact same as the antiderivative of 2 minus 2 on x plus 1 dx. Since there's a subtraction in there, we can separate this into 2 bits. X dx. Let's come over here. Well, the antiderivative of 2 is just going to be 2x minus the antiderivative on 2 on x plus 1. We can, no, that's going to be the 2, and then log e of absolute magnitude of x plus 1 dx. No, we don't need the dx, and we just need a plus c. Yeah, that works. And because this x plus 1, the a in front of the x is technically 1, we're not going to get any divide by here that we need to put in. Well, it's technically divide by 1, but we don't need to write that. So that's what y is equal to. Just the antiderivative. Lastly, following on with this theme of we have something down the bottom, and again VCAR being tricky, is that we need to be able to find the you should say anti-derivatives of f dash of x on f of x. And so an example of that would be this problem. We have g of x is equal to 20 x cubed on 5x to the power of 4 minus 7. If you look carefully, you could say that let 5x to the power of 4 minus 7 equal f of x, and it turns out that f dash of x is equal to 20x to the power of 3, so we have this situation where this is equal to f dash of x on f of x. Now we've seen this before. When we differentiate a log function, we get that. So if we go in reverse, therefore the antiderivative of f dash of x on f of x must be this original log function with f of x inside it. So the antiderivative of f dash of x, we've got this rule. Again, you're not given this rule on the VCAR formula sheet, but if you look at this one and then think of in reverse, you can put an integration sign in there, get rid of that, and that has to hold true, and you just need to stick a plus c in there. Okay. So any of the derivative formulas that you're given in the VCAR formula sheet, you can just write them in reverse by putting an integration sign there. Okay. So in the case of this one, the antiderivative 20x cubed on 5x to the power of 4 minus 7 is log to the base e of 5x to the 4 minus 7. You just stick whatever's in the denominator inside the log. And of course, as always, we need r plus c. So a quick example of that. And the way to notice, we've looked at a couple different ones. We've had one on 80x plus b. We've had a constant on top, ax plus b. We've also, back here, this one, we had 2x. So we had a to the x, or let's put a different thing, maybe ex on ax plus b. Okay. That one, they all become logs. Okay. 1 on top is easy. 3 on top, you just use your scaling factor. This one, to recognize that this was the hidden hyperbola and can just be sort of rearranged, is that it needs to be linear on top. This needs to be linear on top and linear on the bottom. So it can't be x squared, it can't be x cubed. It needs to be linear both top and bottom. That means that's a dead giveaway. It's a hidden hyperbola. And then this last situation is when you're going to have different powers, top and bottom. And straight away, that should be a ringing the bell. If you've got a fraction that you're trying to integrate and you have different powers, this was a linear on top and a squared on the bottom, this should be you're trying to look for f dash of x on f of x. Okay, let's do a check. Let's let 3x squared plus 5x equal f of x. It turns out that f dash of x, if we do that, differentiates, so we're going to multiply by the power and then take one from the power, so we're going to get 6x plus 5. That does what happens to be on top, so this integral is equal to f dash of x on f of x dx. Therefore, it must be equal to the log base e magnitude of whatever was in the bottom. 3x squared plus 5x plus c. So there's your things you're looking for. Is it a 1 on top? Is it a constant on top? That means that you can use just scaling factor. Is it linear top and bottom? It's a hidden hyperbola. If you have different powers top and bottom, then it's going to be an f dash of x on f of x. Now, if you thought that was a lot, and I apologize for the video going a little bit long, VCAR tries to then make it even a bit harder. Okay? And they make it a bit harder where it's not perfectly f dash of x on the top. Okay, so we've just changed, we've taken that we've taken this example here, okay, and we've changed, instead of being a 20, what happens if it's a 5? What happens if it's a 5? So straight away, if you got this problem, you need to integrate this. Well, I've got x to the power of 4, I've got x to the power of 3. Okay, I've got different powers. It's a dead giveaway. I'm doing an f dash of x on f of x. So you're going to let f of x equal to 5x to the power of 4 minus 7. Therefore, f dash of x must be equal to, multiply by the power, so 4 times 5 is 20, x to the 3. Okay, so the top needs to be 20x to the 3, but it's not. So how would I turn 5x to the power of 3 into 20x to the 3, which I need? Well, that's what it's showing here. We don't have what we need, but what I could do is I could times that 5 by 4 to get what I need. But if I times that 5 by 4 to get what I need, well, then I would need to also put a 4 down the bottom. And using our scaling factor trick, that 4 down the bottom, I can instead bring it out as 1 on 4. So that's what this is showing here. It's multiplied the 5 by 4 and given me the 20 that I need. But since I've multiplied it by 4, I need to bring a 4 in the denominator out the front as a scaling factor. And then I get to use my rule. Quite easy. The quarter just stays at the front. I've now got f of x in the denominator and I've got f dash of x in the numerator. So I just apply that rule to anti-differentiate it. So, final couple of examples and that's it for this video. Let's have a look. Straight away, I recognize I have different powers, so I'm going to let x squared plus 2 equal f of x. That means f dash of x is equal to 2x. Yeah. So I need this to look like 2x on x squared plus 2, but I had a 4 on the top, so to convert that 4 into 2, I would have had to divide the top by 2. Or I could almost think of taking it out as a common factor, so I could do 2 times 2x. That's what 4x is. That means I can now take this one out the front. So that's now going to be 2x on x squared plus 2. So a little bit different from this example because I had to multiply the 5 to turn it into 20. This one I had to technically divide the 4 by 2 or just think of it as a common factor. Taking that out, take it out the front to get it as I needed. So I can now use the rule that that is going to be equal to 2 just stays out the front, log to the base e of whatever is in the denominator plus c. Okay. Lastly, this problem here, there's no numerators, no denominator, but this is to again, you're not given the derivative of tans or the antiderivatives of tans on the VCAR formula sheet because you need to remember that tan is technically equal to like opposite over hypotenuse, or tan x is technically equal to sine x on cos x. So I now need to rewrite this as sine x on cos x dx. And so I've clearly got a fraction that I've got different top and bottom. So I'm going to let cos x equal f of x. So f dash of x is going to be the derivative of cos x, which you are given on the VCAR formula sheet. The derivative of cos is negative sine x. We get negative sine x. So I need to make the top negative. So to get negative sine x on the top, well, if I make the top negative, I would then also need a negative 1 there, or I could think about I have to put a negative 1 down there, which again I can take out as a scaling factor. So I could put 1 on negative 1, or much better just if I put negative sine x, well, negative 1 times that. I take the negative out the front, negative sine x on cos x. So now I have it where I've got f of x on the bottom, I've got f dash of x on the top. So that is going to be equal to negative 1 times by log to the base e, absolute magnitude of cos x plus c. Just to simplify it a little bit, we don't need to write it as negative 1 times log, we can just write it as negative log the base e cos x plus c. And we're done. Unfortunately, we have to do all these sort of edge case scenarios because that's what VCAR likes to assess. You're given this. You're given that one. You are given this one, but you are not given this situation, and you are not given this situation. So those are the two that you need to remember off by heart. And also how to remember just that you can have those hidden hyperbolas that can be adjusted. So there's a lot in this video. I apologize. Yes, I've gone to 30 minutes. It is what it is. As always, if you have any questions, hit me up. Thanks and have a good evening.